So we suppose that G, a sigma algebra, is generated by finitely many atoms, and we want to show a representation of the conditional expectation of x given G as a sum over a series of conditional expectations multiplied by random variables. And we're going to do this using the just classic trick of explicitly showing that this random variable, this sum, satisfies the definition of a conditional expectation. And then it will follow by uniqueness that it is, in fact, the one. So let's do that. Let z equal the sum from n equal 1. No, let's call this I equal 1 up to n of the expectation of x given ai multiplied by the indicators of ai. So these ai's are the sets which generate together the sigma algebra G. First, measurability. It follows from the fact that G is equal to the sigma algebra generated by these AIs. It follows from this that for each I in 1 to n, AI, the indicator, of AI is G measurable. Not much surprising there. Of course, the conditional expectation of x given AI is also AI and therefore G measurable, right? So this product of the two is G measurable. And thus the linear combination of them, well, just all of them added together, Z is also G measurable. We really don't have to worry about anything. We're just adding a finite number of them, so nothing weird can happen. All right, now we just need to prove that Z satisfies the integral condition on the conditional expectation. This is a little more complicated, but in the end, just uses kind of simple definitions, not too much going on. So, take arbitrary set B contained in G. Because G is generated by these disjoint sets AI, we know that this B is equal to some union over the AIs. So J is a subset of the integers 1 up to n. That's because a sigma algebra is generated by unions and intersections, and of course the intersections of any of the AIs are empty because they're disjoint. So actually the sigma algebra is only generated by unions. In particular, the random variable indicator of B is equal to the sum of the random variables of indicator of B multiplied by indicator of AI. That's just because the AI's partition G. And this is equal to the sum of all the indexes in this set J, which we don't know what it is, but it somehow is determined by the B of these indicators AI, right? Indicator of B will just be equal to 1 if J is in our index set capital J and 0 otherwise. Therefore, linearity of expectation gives that the expectation of Z multiplied by the indicator of B is equal to the sum over J of the expectation of Z multiplied by the indicator of the individual A. This should be J, of course, not I, what I've written up here above, and also here. That dot, that was a full stop, but it doesn't need to be there. Now, from the definition, let me write that more properly, from the definition of Z and the fact that all the AI are disjoint, it follows that for each individual J in J, we're going to consider this guy on the right hand side, expectation of Z multiplied by the indicator of AJ is equal, just from the definition, as I said, of G, the expectation, sorry, the definition of Z, not of G, sorry, is equal to this sum, the expectation of X given AI multiplied by the indicator of AI multiplied by the indicator of AJ. Let me just make that a bit more distinct. That's IJ, right? That's just putting in the definition of Z. Well, since we are just considering this one particular J here, then the AIs are disjoint. This indicator AI multiplied by indicator of AJ is only 1 in the case that I is equal to J. In that case, this random variable inside the expectation is expectation of X given AJ multiplied by indicator of AJ. And from the definition of conditional expectation, this is just equal to, actually I'm not quite right. I was about to say definition of conditional expectation, but actually this is conditional expectation given an event, not given a sigma algebra. So in fact, what's inside the expectation here is not a random variable, but nevertheless we will get the same result. So this X given AJ is not a random variable, conditional expectation given an event, right? Multiplied by the expectation of the indicator of AJ. But the conditional expectation given an event, we know what that is. It's defined to be the expectation of X and multiplied by the indicator of AJ divided by the probability of AJ. But this on the right hand side is also the probability of AJ, right? So actually those two cancel out and we get what we would have done if we were conditioning on a sigma algebra anyway. So this relies on the fact that each of the AIs has positive probability, which is assumed. Right, she does it. Well, okay. It's not given explicitly in the statement of the exercise that each AI has positive probability, but if it doesn't, then we can just remove it from, we can shrink the sigma algebra and forget about that part. So in essence, it's assumed, but it should be stated really. Okay, final step. What we have, we've shown that expectation of Z multiplied by indicator AJ has this expression, expectation of X multiplied by indicator AJ. And then what we had here is that the expectation of Z multiplied by I indicator of B is equal to the sum over these. So we can return to that. Expectation of Z multiplied by the indicator of B is equal to the sum over capital J of expectation of X indicator AJ. Well, since B, if you remember, is defined to be the union over J of these particular AJs, this is equal by linearity of expectation to be the expectation of X multiplied by the indicator of B. What we've shown then is Z is a G measurable random variable satisfying this equality. Thus, by uniqueness of conditional expectation, Z is equal to the conditional expectation of X given G, right? B was arbitrary element of G, and so we've shown the definition of the conditional expectation holds, and it follows from uniqueness that this must be it.